Thank you everyone for coming to DNS talk. For us, this is a really special moment because it is the very first time that we introduce our work about encrypted DNS. This is the very first talk. We are talking about encrypted DNS publicly. And from the title of the presentation, you can see that encrypted DNS is by itself a huge milestone on privacy and security. But the real novelty of this talk, of this work, is that we are providing the encryption of the DNS communications starting from the installation and deployment through the boot process and obviously during runtime. So at the same time, this work represents another big milestone satisfying requirements from the Zero Trust architecture. It's a huge milestone for RHEL. And where basically nothing is trusted in the Zero Trust architecture. You never trust on anything, and not even DNS. So my name is Francisco Triviño. I'm here with Pavel, Březina, and Antonio Torres. The three of us, we are software engineers. We work at RHEL, but we haven't done all this work alone. And this is a true collaboration among multiple teams from RHEL and true collaboration in all the upstream projects. Just to give you some numbers, we have to modify more than 10 components in the operating systems so that we can implement this feature. So basically, I will cover the why encrypted DNS traffic is so important. With one example, Pavel will cover all the system integration that we did in the operating system in RHEL, and Antonio Torres will cover a use case that is about the EDM and FreeIPA use case that, as you know, it integrates a DNS service as well. So just to get your attention, I will start by this slide. Okay. So the other day, Pavel and I and Antonio, we were trying to watch something from Netflix. As you know, we were starting to see that this is spinning well, it was not working, and we are engineers, so we have the laptop and we started to start debugging what is going on, why Netflix doesn't work, and when this was working, it was really low quality. So yeah, we started to sniff some traffic from the network, capture some packages, and obviously the streaming of the video was protected need to increase my volume. Yeah, sorry. Okay, yeah, I have a strong voice, so no problem. So yeah, this is an example of requirements, and we have another one that is probably coming soon. This is the Cyber Resident Act. This is for the European Nation, and they have their own process based on services that are class 1, typical, and class 2. But yeah, there is another public document. They are not specifically mentioning that everyone must encrypt the traffic, but they are talking about network, and that the network must be authorized and authenticated all over the places. So we understand that we need to certify the requirement for this. And then, yeah. Yeah, all those requirements that we can see from all those memorandums and organizations, big organizations, they fall into the zero trust architecture. It's a set of principles of implementing zero trust enterprise. In simple words, is never trust, always verify. This is kind of what he's telling us. And then among all these requirements, because this is huge, there is one specific talking about the network, is that all the network traffic must be authorized, authenticated, and encrypted. So I will explain about what is zero trust specifically for the network with an analogy. Okay, so in this analogy, if you treat your home like a computer network, once you get in, you are free to go to any room. Okay, so in the zero trust world, that is not possible. You will need to authenticate yourself if you want to detect in any room. So this is what that does. Okay, so this is what follows the never trust and always verify. And this is here I have another analogy. This is this time for non-Python, where then personally saying good morning. So the analogy is that with the zero trust, in every communication you need to prove yourself and who you are. And then this requirement about the network is just a pillar from the zero trust architecture. Okay, as you can see, there are so many pillars, and this is covering everything, all the services and all the infrastructure. You know, and what we are addressing in this work is just one piece of the puzzle. And I'm sure that there are other talks that we are covering other aspects from the zero trust architecture, but the idea here is that our operating systems they should be compatible with zero trust architecture. And we already satisfy many requirements from the zero trust architecture, and we are just focusing on the ones that we don't support, and this is kind of our focus. So we're talking about encrypting the DNS. After some talks with CISA that we had in the past, we came up with a list of requirements. This is a simple one. I mean, the first one and most important is that all the traffic that is ongoing outside of the local host must be encrypted. And another
Thank you. So this one is working? Yes. Can you verify? Great, okay. So hi, I'm Pavel Březina. Well, maybe let's start a little bit with a joke. So do you know why the DNS resolver broke up with plaintext DNS? Well, no, you can't. It's already encrypted. So, but I'm going to talk about how did we integrate into the system, what components were involved, and stuff like that. So I don't know how much details I have to share, but as you probably know, lots of applications, are talking to a DNS server either using a POSIX interface or their own DNS clients. So most applications will probably use the POSIX interface, such as get address info calls that are implemented inside the C standard library, such as glibc. And the implementation looks up the IP address of a DNS server it's going to talk to in etc resolve.conf file. Other applications may choose to implement their own DNS client. They usually use some third-party libraries like CRS, Limb, Unbound, and similar. And they also usually default to etc resolve.conf, or they at least provide a way how to configure IP address inside of a DNS server inside their configuration file. Unfortunately, the POSIX interface does not support encryption at all, and the applications that are using their own DNS client do not usually implement it either. And there is no common interface that could just allow and enable encryption of DNS for all applications in the system, unless you want to patch every single application, which, of course, is not really possible. So we can work around that and use the fact that we can put the IP address of our DNS server inside etc resolve.conf or configure applications that needs to use their own configuration file, and we can set up a local DNS caching resolver. The applications will talk to this resolver over an encrypted channel, which is perfectly fine because this traffic does not leave the host. It all stays inside a single host, so we can still manage and satisfy the zero trust requirements. But the local DNS caching resolver can then forward this traffic into an upstream DNS server using an encrypted channel. So we wrote some lvn.net article. It is published for a few weeks right now, so you can read it if you want more details about the architecture and all the decisions we made. So we now know what this setup we are looking for. We now know what this setup are we looking for. But so we can look into the protocols that we can use. So there are three major players that are standardized by IETF, one of which is DNS over TLS, or DOT, which basically takes the DNS protocol and puts it inside TLS encrypted channel. This is pretty much the same thing that HTTPS does to HTTP protocol. So it no longer uses UDP on port 53, but it uses TCP connections on port 853. You also have DNS over HTTPS, which can tunnel the DNS traffic inside HTTPS protocol. And the DNS queries are then usually encoded inside resource URLs. So this is especially helpful in situations when the firewall rules are not prepared to just allow DOT port, and the DOT port is still blocked with so many other ports. And usually, of course, for obvious reasons, HTTPS port is usually wide open, so we can watch the network and so on. And we can use this in cases where DOT is not available. If we compare these two protocols to plaintext DNS, we can see there is some overhead when establishing the TCP connections and maintaining those, and when establishing TLS encryption. And this is solved by DNS over QUIC. It's there, yeah. So it basically implements connections and encryption on top of UDP and tries to put all the steps that are required to maintain the TCP connections and encryption into a single initiation packet. So if we look into how these protocols are supported in popular DNS resolvers, we can see that DNS over TLS is pretty much widely supported everywhere on both downstream and upstream sides, so we can both receive and forward the request. DNS over HTTPS is usually only supported on the downstream side, so we can receive the request, but we cannot forward it using DOH. And DNS over QUIC is not yet widely supported at all, but lots of upstreams are currently working on it. So for the implementation, we of course would love to support all these protocols, but for the first implementation, we choose to use something that is already available in the Red Hat Enterprise Linux, and that meets the enterprise requirements. So eventually, we ended up with Unbound as the DNS caching resolver, which is capable only of doing DNS over TLS forwarding. So we focus on this protocol. Well, Red Hat is using NetworkManager to configure the network. So naturally, we wanted to provide integration with the NetworkManager to make it a single source of configuration, so other components can just use this one. And we added some new configuration options to set up global DNS resolver, global DNS server address in a way that enforces DOT forwarding. And we also added some options to set resolve mode to exclusive, which pretty much means that all DNS servers that will be either configured or discovered via DHCP on individual connections are just disregarded. So we chose the Unbound as the caching resolver, but we wanted this to be only an implementation detail, so we can switch to other component native feature if we need to, or we can even provide our customers a choice. So we use dnsconfd project as a middleman between NetworkManager and Unbound. So NetworkManager can now focus only on obtaining the configuration, and it will pass it to the dnsconfd using its dbus interface, and dnsconfd can translate this configuration into configuration of specific DNS services. Right now, Unbound is the only one supported, but in the future, we would love to implement also support, for example, for named or even systemd, resolved, and so on. So this is pretty much replaceable. So now we know how we can integrate into the system, how can we enable encrypted DNS on a running system, but the goal, as Triviño mentioned, is not only do it in the runtime, but especially during the installation and during the boot time for stuff, like geolocation, downloading packages from content delivery networks, mounting a root file system from network, or for example, disk, network-bound disk encryption and stuff like that. For this, we need to be able to generate the configuration inside the installer's initramfs, and we also need to provide their custom certificate, authority certificate, because the companies won't be using any public DNS, they will be using their own internal DNS services, which certificates will be signed by custom certificate authorities. So we need this certificate to be already available in the installer and during the installation. So we added a new Kickstart section certificate that can be used to copy certificate into the system, but not only to the installed system, but it will be copied directly to the installer's initram, so it is available also for the installation. Then we need to set some kernel arguments to select and set up the DNS service that we want to use. So we can use the rd.net.ds, set IP address and hostname that will be used to verify the TLS certificate, and use the DNS plus TLS prefix to enforce DOT forwarding. And we should also set the resolve mode to exclusive. So as I mentioned before, this will be used to ignore all DNS servers that will be discovered through DHCP, which we cannot really trust. So this all is then consumed by NetworkManager and dnsconfd dracut modules, and together with the installer, it will produce a configuration in the initram and enable and start all required services. So we just enabled encrypted DNS during the installation, and the installer then copied the configuration also to the installed system and keeps the kernel arguments, so it is available immediately after the system installs, also during the boot process. So yeah, I think this is enough to introduce you to the feature. If you are interested and want to see more details, for example, how to configure a system that was previously installed without encrypted DNS enabled, you can visit the official Red Hat documentation for RHEL 9.6 and RHEL 10.0 versions and guides. And I guess it's time for Antonio to talk about IPA. So, thank you for listening.
Hey, everyone. So what Pavel explained is great for a single host, but in a typical IPA environment, you have some differences. So commonly, you have several clients, and then you have an IPA server. The server can ship with a bind server. So this is a DNS server, and this helps keeping track of all the other clients and other hosts in your environment. So what happens? This is DNS. We need to encrypt it as well. So what we're doing is encrypting all the queries that are being sent to the server, and this is done by shipping Unbound on every client. So all queries coming from that client come unencrypted to an Unbound local instance, and then this traffic is encrypted to bind. The local bind in the IPA server then forwards the query to Unbound, and this goes to an upstream DNS server that has DOT support, also encrypted. So you can see more detail about this design in that QR code, but you might be thinking, why not just have bind do everything here? So this is an implementation detail. Basically, we have some issues with the compatibility with this version of bind that we currently support. It's something that we're going to work in the future, but for now, we're using Unbound locally in the server as well. So, for having DOT in IPA, we needed to add some new options to our installers, both on the client and the server. So, specifically, you need to specify your DOT forwarder. So this is the upstream forwarder in case you want to have one. So this is it would be this server. And then, obviously, it's TLS. You need to handle certificates. Nobody likes to handle certificates. So if you don't want to, these options are not mandatory. You can just rely on the IPA CI system, and this will be handled automatically. But if not, you can use your own certificates. And finally, we have this DNS policy. So this is basically what this does is whether to allow or not an encrypted DNS in your setup. So if you have older clients, maybe they do not support DOT, so you need this compatibility. But if not, you can just enforce it, and every client that is not compatible will simply not work. Apart from IPA, we also had to add new options to SSSD to enable dynamic DNS update using DOT as well. Okay. I'm going to show you an example. So let's say you want to deploy an IPA server. You can use the common command, which is IPA server install, with your common options, and then you add the new options, and you can see that you can just specify the new server. So it's the IPA and the hostname and the policy. And in the log, you can see that it was encrypted. The Unbound, you have a new local Unbound server deployed, and it's working in port 53, so that's the standard unencrypted DNS port. That's because for the local request, you don't need it to be encrypted. And the installer will also handle the Unbound configuration for you. So you can see this is the configuration in the server and the client, and you can notice that the only real difference between the two is the forwarder. So in the server, you will have whatever forwarder you specified during the install. And in the case of the client, it will point to the master. So that's the diagram we saw before. The client will point, the Unbound in the client will point to the server, and then the client will just forward all the queries to the server that way. Okay? And after all, you need as well in the server, for the configuration of the bind server in your IPA server, you need it to point to the local Unbound as well. So that's what we're doing. This is done automatically in the installer as well. So let me show you an example. We are running dig in the client for freeipa.org. You have your query, and you can notice that the query is being sent to this address, which is the Unbound local instance. It's unencrypted, but then if you check the logs in the server, the IPA server, you can see that it was sent to our choice of forwarder, which is Cloudflare's 1111 and port 853. So that's the encrypted DNS port. This means that locally, this is not encrypted at all. So that's only localhost. But once the query leaves the client, your query will be encrypted and will be forwarded all the way through the IPA server, all the way to the upstream DNS server. If you want to read more about this, the guide and all the options in detail, you can check these QR codes. So for what's next, you want to?
So about what is next and what are we looking into now, what we really want to do is to implement support for DNS over HTTPS as well, because our customers, they will decide which protocol they want to use. So initially, in this first version of the feature, we support DOT, but we need to support also DOH because in the end, they will decide which one to use.
And then other things that we might want to look into is about the DHCP. Right now is not capable of discovering encrypted DNS servers. So we would like to, just for completeness, we would like to add the ability to do the discovery. And about the third point, I think Antonio briefly discussed that. I mean, he was mentioning that we are stuck in Bind version 9.18. These are for certain reasons. And ideally, we should move to upgrade everyone to 9.20 because the version of Bind 9.20 supports the DOT forwarding. And then we will not need to deploy Unbound as part of a FreeIPA server or a replica. So we will be able to rely on only one component at the same time. And yeah, we also plan to add more additional backends to the dnsconfd project. That right now it supports Unbound, is the one that is deployed, but in the future we will be able to deploy as well systemd, resolved, among others. So yeah, I think that was it. And I think we have plenty of time for questions, right? So yeah, I'm not sure if I should drop the microphone or perhaps. So the question, if I understood right, is that how we do the failover from the clients. Are we talking about from the perspective of making queries to an encrypted service, but if it's not working, then to an encrypted one? Yes, that's a great question. I think, yeah, I'm not sure, but we implemented the several policies in FreeIPA. So when deploying the server or the DNS service, the integrated one, we can specify a relaxed policy. So the relaxed policy will allow all the clients, everyone, to try with the encrypted one. But if it is not working for any given reason, it will automatically fall over into the unencrypted one. And but this represents a problem, especially for US government customers, where they are obligated to encrypt all the DNS queries. For that reason, we implemented the enforced policy. The enforced policy, it will not work. If a client needs to talk to a DNS and it must be encrypted, if it works, then yes, otherwise it will fail. So I think we are approaching that by implementing multiple policies. Yes. Mm-hmm. Mm-hmm. Yeah. So I think there are more questions. Yeah.
So have you done any performance testing? Is there any
Yeah, that's a good question. Actually, no, we haven't done any performance tests, and no.
Are there any chances of you, once Warlink is made ready, are there any chances of you actually changing dnsconfd to that backend, or is it supposed to be DBus only for now?
So we don't have a, yeah, well, Warlink I don't think is ready yet, but yeah, so, but yeah, it's in our roadmap to look into it, but we haven't checked.
So for the Unbound, I've noticed in multiple of your screenshots, especially in the IPA section. Yeah, right there, that's perfectly fine. So the for others, we are seeing localhost changeable? Or rather, can I configure and I'm dealing with Unbound, right? I've seen all of the configuration options provided by kudos for that. I can't imagine just how much work went into this. This is absolutely amazing. One of the first things that I'm seeing, because the last object is always the same, is that a deliberate choice, or does the Unbound run on participate 0.0.0.55, or can I change
It's just a choice, but you can. Oh, it's just our choice, the default choice, but you can change it. Just toggle the Unbound config and the server, and you're done. There's no. Yeah.
So basically, yeah, not bad. So yeah, basically, yeah, our installers are deploying the components and writing down the proper configuration depending on the options that we are giving in the all the arguments. Yes. So yeah, more questions. Oh yeah. So we have a bug in the slide. So you're talking about the forward policy first. Only. But this is the server, right? Yeah. So we have another. It should be only. Yeah. Nice. You found a bug in the slide. Congratulations. So yeah, basically, yeah, the thing is that in the FreeIPA server science, by 9.18 is not capable of forwarding the DOT request to an upstream DNS, encrypted DNS server. We had to rely on Unbound, so we are deploying two components. One by as authoritative service for all the IDM deployment. It will resolve all the encrypted DNS queries from the clients, from the topology. But for all those DNS queries that are going outside of the deployment, what we are doing is to forward them to Unbound locally, unencrypted. And Unbound is responsible for making the DOT forwarding to the upstream server. So this is kind of a trick that we did in order to support this scenario. But as soon as we move to by 920, since by 920 supports DOT forwarding, we will be capable of removing this box from here, this component for the server part. We will be able to rely on only by 9. And then all these forwarding policies today will change again. Yeah. Yeah, so the question is, how was the experience working with NetworkManager? Well, it was a challenge because, you know, the majority of the changes there for NetworkManager, you know. So I remember that Pavel and we had to convince NetworkManager people to work on this feature. But we explained the use cases and that this is huge. I mean, we need DOT because of all the memorandums that I was sharing. I mean, this is going to be mandatory for them to deploy that. So they understood the use cases and then they gave the right priority. But in the end, it was really nice to work with them. And the implementation network manager is very important because it's kind of the center place where to handle all these things. You know, the configuration path starts in network manager that is talking to dnsconfd, that is talking to dbus, and then Unbound. So, yeah. More questions? Out of time? Well, maybe we have just more time for another question.
Can we throw away all the equipment and use dnsconfd to configure local caching with all this finally have a locally local system and all of that to install things like SSSD caching? Does not the SSSD doesn't have any DNS caching? And that's
So I'm not sure if maybe you.
I think we can talk on the hallway. Will be better. Right?
Yes, we are available after the talk, and also we will join the social event, so we will be there.